Hi, welcome back to the Block 74 Apollo Guidance Computer set of videos. Today in part 12, we're going to continue talking about the X register. Um, may have noticed that I didn't post a video last week. I was out on vacation, but we'll pick things up where we left off. In our last video, we talked a bit about the X register and how the various pieces of data are loaded into the X register. It is a bit different in that it doesn't load data directly off the write lines. Is used to load a couple of these constants, +1, -1, +2, a few others, as well as some different mechanisms to get data into that X register. The next part we're going to talk about is the arithmetic unit of the Apollo guidance computer, which operates on both the contents of the X and Y register. As we get into a bit of the details, you can sort of see the description here is that the arithmetic unit is a 16-bit parallel adder with end-around carry. End-around carry is used in certain cases with two's complement and one's complement mathematics, where basically you overflow one way or the other. Basically, you wrap around the digits when you start looking at negative numbers. So this end around is actually activated and deactivated based on a couple of scenarios, depending on which operation specifically you're conducting. We can talk about, sort of see that the adder processes two numbers at the same time. One number is contained in the Y register, which we've already talked about, and the other quantity is entered into the X register, which we talked about in the last video. So we talk about, like, during the multiply instruction, the adder is switched to perform basically addition in a two's complement system. So most of the time the AGC is one's complement, which makes it easier to do subtraction. You can basically just invert the contents of the register to produce a negative number, and that's what the B/C register does. We have the inverters on the B register that provide the C or complement register of whatever contents are loaded in B. But in the case of multiplication, we do need to kind of enable this N neocon, which is not or no end around carry. So basically, we turn it on to turn off the end around carry, and then we have neocoff, which basically turns off the no end around carry, which basically means we allow end around carry to occur. So that's one logic, and we have to kind of store that in a particular flip-flop that stores this neocon state. It talks about here around like T10 of subinstruction MP0. We don't need to worry about this too much, at least at this point, because that's tied to the control pulses and basically the subinstruction sequences. So at T10 in subinstruction MP0, we'll actually set this neocon flag or signal control pulse, which we then use to set the flip-flop, and then we reset it as part of T6 of subinstruction MP3, which is another component of the multiply. We also talk about the carry gate output for each bit position is applied to the next high order. So this is basically where we do carrying as kind of how the adder works. And then we've got a little bit more where it talks about the that no end around carry flag. And then we also have a control pulse CI, which is to set a carry flip-flop. So we can manually set our input carry bit. So let's take a quick look at it. Before we get into the schematic, I'm going to just look at basically how an adder works. So here we have basically a logic diagram of what's called a full adder. So a full adder allows us to basically have a carry in bit. So we have our A bit, which is one of our operands. We have our B bit, which is our second operand. And then we have our C in or carry in. Now that's the difference between a full adder and a half adder. A half adder doesn't have a carry in. It just has our carry out. So those are the two outputs of an adder. Is you have your sum of basically the two operands, and then a carry out. So basically, essentially, you have the scenario here. We'll like zero everything out. So this is, in this case, we're using positive logic. So a 0 is a 0 and a 1 is a 1. So if everything is 0, we have a sum of 0 and we have a carry out of 0. If we set any one individual bit, we will have a sum of 1. And if we set 2 bits, we set our sum back to 0 and we have a carry. And this is one of the challenges you see when you use binary logic is that you get carries very, very easy. In our normal day-to-day 10-base mathematics or counting system that we use, the only time we get a carry is you get all the way up to 9, and then once you exceed 9, then you have to do a carry. But in binary, where we only have 0 and 1, basically your count is 0, 1, and then 1, 0. So you move to the next highest place in the counting system. So it means you often have a lot of carries when it comes to doing binary addition. So if we have all 3 that are set, so we have A is 1, B is 1, and C is 1. So this is basically 1 plus 1 plus 1, or 3, which is low bit of 0 and a high bit of 1. So we have a carry. So when you build a adder, you basically, for every bit, you have to have this logic to add the bit. And then you have to, basically tie the carry out of, say, bit 0 into the carry in of bit 1, and the carry out of bit 1 into the carry in of bit 2, and so on and so forth. Now, this kind of, at least in the kind of two extremes. So if you look at the Apollo guidance computer when it was first built, the integrated circuits that used those NOR gates, those three integrated circuits that had three input NOR gates, it was kind of at the edge of the performance capabilities of that era. And it's the same challenge on like modern microprocessors, which are also running at near the edge of the kind of performance of the various logic and gates within a particular microprocessor. Because what'll happen is if you have an adder, 8-bit, 16-bit, in modern processors 32 or 64, is that in order for you to actually complete your sum, the carry bit has to cascade all through every single bit. So in kind of the worst case scenario is where you have a binary digit that's containing all ones, and then you add a 1 to it. Basically, a 1 plus the 1 will mean, oh, we have a 2, we've got a carry, which means you move over to the next position, 1 plus a 1, a 2, carry, and you basically carry every bit along the entire word size of your processor. So that means you've got to potentially propagate that carry bit across, in case of the Apollo guidance computer, 16 bits, in the case of a more modern computer, 32 or 64 bits. Now, this can cause a delay because it has to propagate through all of those different bits in order to produce the final, the high order bit is the final sum. So in the case of the Apollo guidance computer and modern computers, there typically is logic that's applied to try to predict those kind of carry flags in certain subsections. So we'll, for example, look at, okay, of these 4 bits, should we produce a carry out of these 4 bits into the next 4 bits, and so on and so forth, so that you can reduce, instead of potentially in the Apollo guidance computer propagating all 16 bits, if you break into kind of 4-bit blocks, you'd only potentially have to propagate it 4 times down. Now, in the case of what we're building, we're fortunate that we can use full basically adders that are 4-bit adders that are designed to basically do the addition across 4 bits, but they also do this kind of predictive logic in order to generate the carry bit faster. And as well, because we're only running the Apollo guidance computer at a little over 1 megahertz, for the logic that we're using, that's fine. It propagates through that logic fast enough that it's not a concern. But as I said, on the original Apollo guidance computer, they had to do some fancy logic design to make sure that the carry would be able to propagate through all of the bits fast enough to be able to produce usable results. And it's also something that most modern computers also have to deal with because it is an issue. Now, if we flip over to the schematic, and this is kind of a building on what we covered in the last video. So here we have our inputs into the X register. We have the X register itself right here. So this is where we either bring in our contents from our A register, or based on the control pulse, we load it with a +1, -1, +2, etc. That information then gets stored into the actual register itself, so that on our write pulse, it's loaded into that particular register. Of course, we have our LEDs, so we can show what our contents of our X register are. And then what we have here are our adders. So we're using the 74LS283, which is the 4-bit adder. And so we have our two operands. We have our A kind of input here, which comes from our X register. We have our B operand, which comes from our Y register. And then you can see we basically cascade our carries. So basically the carry out goes to the carry in, and so on and so forth, all the way down for our 16 bits. Now, in our next video, we'll talk about kind of the part of the diagram over to the right. We have to do some of the same write bus ORing that we do with our A register, because there are certain control pulses that basically bring in data from the write bus and need to add it to the contents of our summer, basically the sum that comes out of the adders, in order to push that onto the write bus. So that's very similar to what we had to do on our A register. So we'll cover that in the next video. But what we do here, like I said, we've got our kind of cascading carry all the way down to we have the kind of the end where we have our NIAC signal, which is we basically determine whether we need to carry, basically do the end around carry, which is all the way from the high bit 16, all the way back to bit 1. Now, in addition, we also have our CI register, where we can store that carry based on the CI control pulse. So what we have here is we have the logic of the CI pulse comes in. We invert it because, of course, we have our negative logic on control pulses. We store that carry in the flip-flop, and we can then combine it, whether when we have our carry, either the carry comes in from our carry bit or it comes in from our end around carry, and that provides our carry in for bit 1. Some of the logic that we had talked about in the last session is that there are certain scenarios where we have to clear our CI register. So some of the write pulses that go to the Y register, WY, WYD, and WY12, what they do, not only writing data into the Y register, is that they also reset the CI register, or the CI flag or carry in flag, so it can be potentially set based on other operations as part of the sub instructions that are being executed for various instructions. You'll notice here that I have, on this kind of NIAC pulses, like, okay, well, where does this come from? Is just to make things a bit more efficient from a space perspective. I found that I had some extra basically real estate on the circuit board for my Y register. So I decided to implement the NIAC register on my Y board. So I have my NIAC on signal, my NIAC off signal, and then that's kind of used to either set or reset this flip-flop. which then generates our NEX signal that we can use on our X register. The reason I did that is that, because we have the adders, and then we have the ALUs to do the logical ORing for the write buses, plus a bunch of control logic, both on the input and output side. The X register, from a circuit board perspective, starts getting fairly complicated. Now, I did just receive my second set of boards that I'm using to build the computer on, and I did make the second set larger, so I can the originals I could put up to 25 chips onto a single board. The new one I can now put 35 chips, so they're a little bit longer. So I can fit some of the more complex boards like the X register, and then as we get into the G register, which is also quite complex, and then the S register as well, we'll be able to have plenty of space on those boards to be able to build them out. So that is what I have for today's discussion around the adder and the arithmetic unit within the Apollo guidance computer. It is kind of neat where you can see how a adder can be used to perform pretty much all of the arithmetic functions that we need. We can use it to provide addition, of course. Using the C register as a complement, we can provide subtraction. And then in order to do multiplication and division, we use a combination of the adder as well as shifting. Basically, every time you shift a bit to a higher order, you're multiplying it by 2. Whenever you shift it to a lower order, you're dividing by 2. Anyway, I'll have a new video out in the next week where we'll talk about kind of wrap up the X register and how that kind of reads and ORs the data back out onto the bus. There's a few variants around what they call, there's a RU, which is kind of read out the sum, and then there's a RUS, which does a few other different things. And then there's also some mechanisms to write the contents of the summer or the adder, the sum register, into aspects of the fixed bank and the extended bank for memory storage. So we'll start talking a little bit about how memory is arranged within the Apollo guidance computer in the next episode. As always, please subscribe if you want to follow along. Feedback is always welcome. Always look forward to any corrections that people might have or questions that folks have on what we're doing. And I am, as I start to get each of these schematics more mature and more complete, and I've built the boards and started testing them, I am going to start publishing them to GitHub. So if you do want to follow along and poke around in the schematics that I've put together, those will be available probably in the next week or two. So you can, I'll add the link into the show notes and you can follow from there. Anyway, thank you again, and we'll speak to you in about a week.